So, all right, so let's get started. So this is the last lecture this semester. We're going to do a review of, so everything in the, in the class this semester. So again, the plan is to go over everything in this practice exam that's linked off of, the last line of the schedule there. So we're going to go through all the questions in there. That's, the main thing. I'll do a little bit overview first. So don't forget, so homework 5's due tomorrow. We'd like to be able to, tell you the answers if you ask, and so we can do that 2 days after the late deadlines expire, which will be Sunday night, I guess. The exam is Monday, right? So it's the we've got one of the early exam slots this year. We will be here in this room with me and a bunch of the TAs will be monitoring on Zoom at that time to answer questions. It is open until midnight. You'll have 2 hours once you start. So again, as I announced on Tuesday, the exam will be on Canvas, and it's going to be set up as a Canvas quiz. Again, you have 2 hours. I'm gonna set it up so the questions are gonna be sequential. So you're gonna be able to only do one thing at a time. We put a lot of thought into this, and I think this is the best option. And I think you will appreciate that at least after you take it. I understand that makes you nervous because then if you're not sure about how to answer a question, you can't defer it until the end. I will work hard to try and make sure that you're not time constrained on the final. Okay, so once you start in motion, Canvas does not give me a mechanism to allow you to go back to something, which I would let you do in the room if I could. I do have a mechanism where I can give you a little bit of extra time, so I don't want you to be time rushed on the final. Okay, so if you're in the room and you're like, look, I'm falling a little bit behind, I'm like, look, I can give you a little bit extra time, but I can't let you go back to the question. So answer questions, one at a time. I think I'll try and set up, we're still making the final, so I can't 100% promise it, but try and set up so it's easy to keep track of time. And you'll probably, stay ahead of schedule. I'll post something on as an announcement with some more details once things are more finalized in the structure. But it will kind of be like the quiz questions. They will, it's going to be the main takeaway points that you should have gotten out of the course. Okay, and if you look at what the main learning objectives you're supposed to learn in the course, those are the main things I'm going to be testing you on. So there are a lot of more nuanced points we got into throughout the semester. You're not going to be asked on those like very nuanced points that we kind of got into to give you more depth about stuff. Okay. Any other kind of structural questions on the exam? So great. So then we'll, let's get into the review. All right. I'm going to go through the questions just like, just one by one. Before I do that, I want to remind an overview of kind of this chart I drew at the start of the semester, and hopefully this makes slightly more sense now. There are kind of these 4 quadrants of the class of the techniques the kind of data analysis approaches that we looked at. There is the supervised. Okay, and this is where the input was basically X in RD. Okay, so we're just given a point set. Whereas supervised is where the input was this pair X and Y, right? Where these things are so labels. Okay. Okay, and then there are two types of rows here. These are where the output is so real values. Okay, in R, and these are where the output is a set. All right, and so if you look in these, what is where there's a supervised where we're given X and labels Y, and the labels are the output, so the real values. So what goes in this first box here in the upper left corner? This is going to be so this is going to be regression, right? And remember, this is where you have X here, and we can think of Y here, and we're building some sort of function, right? This is a function that went from some point X and mapped it to, so like some prediction Y, okay? Right, so then what would be in the lower part here in the first column, where again we have labels, but the output is a set, right? So this is the case where we have the set output, the Y, is where we said there are only two options. You can make this more options, but in the interesting case we're looking at it most of the time is two options, pluses and minuses, right? And the output, then is going to be this function, right, where we classify everything on the positive side as pluses and negative side. So this is classification. Okay, when the output is a set or a class, you classify. Okay. All right. So when we're unsupervised setting, then when the output is a set, we're just given data objects and we need to group them into sets, but we don't have labels, right? That's the case where we just have points, right? And we want to somehow group these into these sets, right? So then this was clustering. Okay, and then what's left is dimensionality, reduction, right? And so here we have points in some high dimensional space, and the goal is to find this line which is close to all the points. So if I project them all orthogonally onto here, right, then I can find the best line that is close to all these points, right? So that is, it's unsupervised. I don't have the labels. Okay, and the key thing to remember is in this supervised case where I have these labels, then I can do cross validation, where I can evaluate how well I'm doing. I can choose parameters. I can measure against the actual values that I'm trying to predict these values. So I get an unseen X, and I try and predict the value Y, either from a set or from like a real value. And I can evaluate how I'm doing with cross-validation, or I can tune parameters with that, right? So those are the two things you can do with cross-validation. Okay, and so the supervised ones, I have this extra way of, these are much more powerful in terms of how much they're used inside of data science in general, because I have a fixed goal. I want to predict the value Y. The unsupervised ones, those are kind of like used more behind the scenes and pre-processing and understanding the data, but I'm not guided as much. I'm not supervised in the process. So I'm kind of just trying to find the structure existing in the data. Okay, and this is the main kind of categorization of both of them. Okay, so this was in the first lecture. You're seeing it in the last lecture. Hopefully it makes a lot more sense now. And if not, I haven't done a very good job of the course, but I think I promised you it would make more sense at the end of the semester. So hopefully that's the case. Okay, so let's go on to the actual questions. All right, so let's just kind of go through these. This was on the basics of probability. Just make sure you understand kind of basic probability. Again, we looked at this through tables. In this probability table, what's probably x equals 1? You know, this is going to be 0.1 plus 0.3, which is 0.4. Right, so this is what I would expect to see. Okay, it's just this first column here. Okay, the next one is x is equal to 2 and y is equal to 1. Right, so that means I need to look at both the row and the column, and this is just 0.05. It's just when those are both true. Right, and if x is equal to 3, but I know y is equal to 2, given y is equal to 2, well, then I need to restrict to looking at kind of, I'm restricting myself to looking at this column here, and I want to understand x, because that's given y is equal to 2, so that row, I know I'm in that row, and I want to know the probability x is equal to 3, given that I'm in the row. This is a little trickier. I need to say this is 0.2. That's the probability that they're both true, divided by the probability that y is equal to 1, and that's 0.3 plus 0.25 plus 0.2. You could probably leave it here, but if we were to write this out, that'd be 0.2 divided by 0.75, and it's a probability that's between 0 and 1. Okay, good. What is the marginal distribution for x? Okay, the marginal distribution says the probability just based on x, ignoring y. I want to marginalize out to y, right? So I just kind of for this one, I'm just going to kind of write something in the margin. This is now the bottom margin, 0.4, 0.3, and 0.3. Right, so that's the marginal distribution. That's here. Was the conditional probability for y given x is equal to 2? Right, so the probability for y given x is equal to 2. Now I'm going to be looking at kind of this column, given x is equal to 2, then I can write a table for y is equal to 1, y is equal to 2. Those are the two cases. And it's going to be I divide by the marginal. So 0.05 divided by 0.3, and this is 0.25 divided by 0.3. Okay, again, you can check that those should add up to 1. Well, I didn't actually calculate them, but I can check they add up to 1 because the numerators add up to the denominator. This was by design. Okay, that's the conditional probability for y given that x is equal to 2. Okay, so it's a probability table. Okay, are random variables x and y independent? Okay, to check if random variables are independent, they have to be independent if all of the events are independent of each other. So one thing I can do is I can compare let's see, how would I do this? I can look at so x and y are independent is the probability for x is equal to 2. Let's say x is equal to 2 times probability y is equal to, say, 1. This should equal the probability that x is equal to 2 and y is equal to 1. Okay, so let's check this one, right? So I know x is equal to 2 is 0.05. That's the marginal, so 0.3, right? So that's probably x is equal to 2. Probably y is equal to 1 is equal to the sum of the first row, right? So that's 0.25, right? And the product of those, the question, are those equal to x is equal to 2 and y is equal to 1? 0.05. Okay. Let's see, this is 3/10 times 1/4. This is equal to 3 out of 40. That's 3 out of 40. 0.05, what is that out of 40? Is that, is it, so 2 out of 40? So these are not equal. So the answer is no. Okay, so you can find an example and check an example, and it has to be true for all examples. If it's true for all examples, that's a bit trickier to prove, or a bit trickier to show. Okay, usually you construct them or you assume random variables to be independent if you want that to be the case. If you have a probability table, you need to kind of check everything if that is the case. Okay, is x is equal to 1 independent of y is equal to 1? Okay, this is an event, and this could be true even if the total independence is not true. So we can check that now. Again, the probability that x is equal to 1, this is, we calculate this is 0.4. Probability y is equal to 1, this was 0.25. 0.25, we calculate that from here. Okay, and the product of these, 0.4 times 0.25, right? This is equal to 1/10, and this is equal to probability that x is equal to 1 and y is equal to 1. So the answer for this is yes. Okay, so events can be independent even if the random variables are not. Okay. Okay, yep. Is 1/20. Great, which is 2/40. Perfect. Thank you. Right? 1/, oh, this is 4/10. So this is 4/10 times 1/4. Isn't that equal to 1/10? Think, yeah, so if you were to write this out and you would come to the wrong conclusion, we would try and give you full credit for it. Sometimes calculation mistakes happen, but so I think everything's right, but this is at least how you would approach the question. All right, clear on this? Key things are independence, conditional random variables, or the understanding what the conditional probability is. But a question with a subset of these things you could do in like 10 minutes, right, on the final, right? Okay. Okay, two models, M1 and M2, where from prior knowledge we believe the probability of model M1 is 0.25, probability of M2 is 0.75. We observe data. Given each model, we assess the likelihood of seeing the data given the model, right? Here, the data given M1 is 0.5, data given M2 is 0.01. Now that we have the data, which model is higher probability of being correct? What do we need to do here? What rule do we need to use? Yes. So this is a Bayes rule question. Remember, this is probability of the model given the probability of the data is equal to the probability of the model given the data times the probability of the data. This is, I've got this. I'm writing this up, but I'm swapping the normal. Right. So let's see. So I want to say the probability of the. Oh yeah, here that one was wrong. Okay. Probability of the data given. So the model times the probability of. So the model divided by the probability of. So the data. Okay. Good. Bayes rule, probably a good thing to write down your cheat sheet, just in case. Okay. Right. Okay. So this is Bayes rule. We need to plug this in. We have, remember, we have these and we have these. We don't have this one, but we just need to compare them. That's going to be the same. Probably the data is going to be the same, right? So we're going to write down the probability of M1 given the data. It's going to be equal to the probability of the data given M1 times the probability of the model divided by the probability of the data of M1. Okay, so this is going to be equal to the data given model. This is 0.5 times 0.25 divided by the probability of the data, which we don't know, but we're just going to compare. And similarly, probability of model 2 given the data is going to be 0.01 times 0.75 divided by the probability of the data. Okay, so this is going to be 0.125 divided by the probability of the data, and this is 0.0075 divided by the probability of the data. Okay, and we don't know what the probability of the data is, but we just need to compare them, and this is 0.125 divided by some constant. This is equal to 0.0075 divided by some constant here. And so this one is, you know, M1 is larger. Okay. So this seems pretty straightforward. The key is to identify that you can use Bayes rule. If you write down, you know, if you have Bayes rule, you can do this calculation. It's not too hard. It's probably, you know, this is probably the limit of the amount of calculation we'd ask you to do on a question, to do something like Bayes rule, putting in the numbers for something like this. Okay. Okay. Question 3. So I have 3 data points, x1, x2, x3, drawn ID from an unknown function. Okay, given a model M, I calculate the likelihood that each data point, you know, the likelihood of each data point given this model, 0.5, 0.1, 0.2, was the likelihood of seeing all these data points given the model M. Probably x1, x2, and x3, right, are observed given this model N. What is the key thing to identify here? Yep. Yeah, so IID, what do I need particularly about the IID? So what does IID stand for? Yeah, so it stands for, so independently, identically distributed, right? Independently, identically So distributed. Okay. Identically distributed, so they're from the same distribution, right? And that's this unknown distribution that's probably implied by the writing. But the independence is what's really important here. The independence of these observations means that we can write the probability of x1 and x2 and x3 given a model as equal to the probability of x1 given the model times the probability of x2 given the model times the probability of x3, so given this model. This assumption underlies how we analyze data throughout the semester, right? We think we have data points, we think they're independent of each other, and we can kind of write down the likelihood of some model is somehow a joined likelihood. It's the product of all these, and through some log transform it becomes a sum, and we get these cost functions, which are the sums of costs from each of the data points. Okay, this is kind of, we always make this assumption, right? But in this case, what it allows you to do is to calculate this probability, right? So now I have 0.5, 0.1, 0.2, or 2. Okay, and I just take the product of these things, and this is 0.001. I think that's right. Yeah. 0.01. Okay, good. Yeah. Okay, good. So that's the answer here. Key is to identify that these are independent, and the independence can turn a joint likelihood into a product, right? The probability table did not assume this, but in general, in a lot of data analysis, we assume this, and so that's what I want you to like identify here. Okay. Okay. Okay, consider a PDF F. So a random variable x is drawn from F. Its expected value is 3. Its variance is 10. Now consider n IID random variables, x1 through x10 from F. Let x bar be the average of these random variables. Okay, and then a bunch of questions. What is this question about? What is the main topic from here? Some theorem that we're gonna. So the central limit theorem, yeah. We want to identify that this is the, so this is the central, so limit theorem. This is the setup of it. And what it tells us are the expected value of x of x bar is the same as the expected value of x. The variance of x bar is equal to the variance of x divided by 10, and that in the in the limit that as n goes to infinity, that this approaches some sort of normal distribution. Okay. Okay, so this central limit theorem, and if you remember this and identify this, well, then the first two questions are very easy. This is the expected value of x, which is 3. The variance of x bar, well, this is the variance of x var x divided by 10, which is equal to 1. Okay, so the first two questions are easy, right? I have some trickier questions on, the third question, standard deviation of x bar. Standard deviation of x bar is the square root of the variance of x bar, which is equal to square root of 1, which is 1. Okay, that one also should be pretty easy. D and E are a little bit trickier. Okay, so this one you need to draw a picture to think about. Okay, we're going to say the expected value is 3. And so what do these distributions look like? The distribution for x might look something like might look something like this, right? So this is f of x, and then I have another distribution for x bar, something like, okay, they both integrate to 1, but x, this is f of x bar. This is more concentrated. It's got the same expected value, so the center of them is about the same, but the variance is smaller by a factor of 10. So the standard deviation is smaller by a factor of something like 3 roughly. And so these are the picture. And now the question that is asking, so it helps to draw a picture like this. The first one's asking about 4. So let's say there's a value 4. What's the probability that x is greater than 4? What does that look like in this picture? The probability x is equal to greater than 4 in the picture is everything up to here. Okay, so this is the probability. This is the probability that x is greater than 4. It's the area under the curve after 4. Okay, and what is the probability that x bar is greater than 4? It's just this little spot down here. Okay, so this is the probability that x bar is greater than 4. I don't know exactly what these are, but I need to say which one is larger. From this picture, which one looks larger? Which has more area? The light blue or the green? Yeah, the light blue. And I will generally know that this is true. The blue one is larger, so the answer is this. X greater than 4, probably x greater than 4 is larger. Okay. Now I need to do the same thing with a different question for 2. Right, so now I look at this for the value 2, and I say which one is larger now. Well, this is equivalent to saying which is smaller, p of x less than 2, or less than or equal to 2 technically, p of x bar less than or equal to 2, right? These are equivalent because the probability is either greater than 2 or less than or equal to 2. And I've switched larger to smaller. And now it's the same question, except it's the other side of the mean, right? So now I can say which is larger. Which one is now larger is, which one is smaller? It's going to be x bar is smaller, which means this one is larger. Okay? I did the same thing as before. I can see this area is smaller than this area, so I identify that smaller. Yeah. Well, I could also draw pictures like this. I know that yeah, this one requires a little bit of thinking. This is kind of more of a challenge problem. You know, I'm not saying I can't ask a question like this on the final, but if I did, I would try and give you lots of hints, right? But if you understand this, you know, if you get a question like this, try and draw a picture, think about the areas under the curves, think about swapping it, try and find an easy way to analyze this. All right, any questions? The
variance of x bar divided by 10 because x bar is the problem of this one.
The 10, good question. This 10 here is from the ID random variables. Yeah, this is divided by, yeah, I should have said this is equal to n. Right. Yeah, so that's what the central limit theorem is. Yeah. And the variance divided by not the standard deviation. The standard deviation, easier to think about because it's the same units as the data. but the variance is easy to do some calculations with, right? The sum of squared errors is basically a variance. That's why we calculate that. But the square root of that has the right units, right? So that's why we have both the standard deviation and the variance. One's easier to calculate, one's easier to think about after calculations. Okay, great. Question 5. Oh, yep. We don't know. We do not know it's exactly normal, correct? When we draw. Yeah, yeah, so there are other ways I could ask you this question where you wouldn't necessarily know the answer. I've chosen to ask it in a way so that you can reason about it, even without it being normal. It will concentrate, which is going to bring the variance in. And basically at every level, it's going to be more concentrated closer to the mean when you have the average, as you don't. So it's fact that you can measure stuff against the mean is what's happening. Yeah. So yeah, if I'd asked this differently, you may not have been able to answer it, but I was careful how I asked the question. Yeah. Okay, let X be a random variable, so you know is in the range -1 to 2, and you know has expected value of 0. Use the Markov inequality to upper bound that X is greater than 1.5. Okay, so we need to identify this is a Markov inequality question. Markov inequality, let's say we used X, so let's say Z is a random variable. Yeah, so we have the Markov inequality. You have a random variable Z, and you know that you know two things. You know that Z is always greater than 0, and you know the expected value of Z. Okay, so this, we want to apply it. If we have this property, then we know that the probability that Z is greater than some alpha is less than 1 over alpha. Yeah, is it less than was the expected value of Z divided by alpha. Yeah, okay, so this is what we have to work with. And we want to apply this, and we have a random variable X. Okay, it doesn't, you can observe that it does not satisfy this quantity. We cannot just use X is equal to Z and apply this. We want to answer this question, you know, and that matches here. That's good. So it's the right sort of question to ask, but it doesn't satisfy that X is greater than 0. But luckily, I provided a hint. You'll need to use a change of variables here. Okay, so change of variables, change of random variables. What we're going to do is we're going to set Z is equal to X plus 1. Okay, so now we know that Z is now going to be in 0, 3. Okay. We also know the expected value of Z is equal to the expected value of X plus 1. And by linearity of expectation, which is another important thing you should know, this is expected value of X, which is 0 plus 1. So this is equal to 1. So now we have the expected value of Z. Okay, and Z satisfies this rule for the Markov inequality. Okay, now we need to answer the probability that X is greater than 1.5. So we need to translate this into a question about Z, and I can add 1 to both sides. So Z is greater than 2.5. I've added plus 1 plus 1 on both sides. Those are equivalent. And now I can apply the Markov inequality that this is the expected value of z, which is 1 divided by alpha, which is 2.5, right? So this 2.5 is here. Okay. Let me redo share screen. Okay. Sometimes that happens. All right. Okay, great. Okay, and so this is the answer. Right? So the answer is then 1 over 2.5, which is, what is that, 0.4? Okay, so that's the answer we want there. Okay, so identify Markov inequality, see if it fits. If it's Chebyshev or Chernoff-Hafting, you have these rules that you need to follow in order to apply it. Make sure it satisfies that rule. You may need to do a change of variable. Also, we looked at the linearity of expectation here. Yeah, so this is linearity of expectation, linearity of expectation. Right, so this is also a key thing. I can factor out scale multiples and additions from the expectation. Yeah. Yeah, I'm applying the Markov inequality, which is written here, to the random variable z. Right, so the alpha, I'm going to set alpha equals to 2.5, and then I can plug that into this expression here. Right, so the probability that z is greater than alpha is 2.5, is the expected value of z divided by alpha, which is 1 divided by 2.5. This is the expected value of z, and this is alpha. Okay. Yep.
So so for the requirements for the Markov inequality, it's not that the variable has to be strictly greater than 0, because in the case like our
yeah, it can be greater or equal than 0. That's fine. Yep. Yeah, so greater or equal than 0. Yep.
And does it matter how much you change?
Well, if you could do this with z is equal to x plus 2, right? That's going to give me a valid upper bound. What's going to happen if I use x plus 2? This is I'm going to get the expected value. Then this would be, let's say z prime is equals x plus 2. Expected value of z prime is going to be equal to 2. Okay, and now this is, I want to bound the probability that z prime is greater than 3.5. Okay, and now I'm going to get, and the bound I'm going to get is now going to be 2 divided by 3.5. Okay, is this bound better? This is going to be 2 divided by 3.5. That's 4 divided by 7. Right, it's 4 over 7, which is, that's like 0.43. What? 57. Oh yeah, 0.57. Okay, so what's happening here is I say the probability x is greater than 1.5 is less than 0.57. I also know it's less than 0.4. Okay. Well, it's less than 0.4 and it's less than 0.57. So this is more useful. So that's a more useful bound. They're both correct bounds, but this one is more useful, right? So you'd like the random variable to have some probability mass at 0. That's when the Markov inequality is the most useful. Okay. So if I have this extra gap, it does not help. And you can try adding a larger value there, and you'll see eventually it gives you an upper bound of 1 as that as what you add to it goes to infinity. And that's even less useful. Okay, great. So let's look at the next one. Okay, question 6. We're into the linear algebra. A is a matrix. I'm not going to read all the entries. It's got 4 rows and 3 columns. Add a column to A so that it is invertible. Okay, what do we know about invertible matrices? What does the matrix need to be invertible? It's to be square and has to be square and does not need to be orthogonal. If it's orthogonal, the inverse is easy. So that's good. That makes if you wanted to compute the inverse, then orthogonality would probably be a nice property. The diagonal also makes it easy. What? Yeah, so in general, the columns have to be linearly independent. We would say full rank often. But so if the columns are linearly independent of each other, right? So what this means, yeah, so the columns have to be linearly independent. That means that I can't write one column as a linear combination of the other columns, right? By adding scaled multiples of the other columns. Okay, so I need to add a column, so that's not true. First, let's check, are any of the columns linearly dependent on each other? If that was the case, then it would be rank 2, and I'd need to add at least 2 columns. Or even if I added a column, it could never be invertible. But I think I set that up so it's not the case. So I need to add a column so that it's going to be invertible. What's an easy way to do this? I'm gonna, what? Prime numbers or some random, like decimals, like 0.003, 4.26, pi, and e. Okay, good. That's gonna be pretty invertible. Okay. Yeah. Well, imagine. Yeah. So, yeah, if it's imaginary, it's I don't know. I forget that part of linear algebra because I've never had to use it. But I try to avoid imaginary numbers. Yeah. Don't put imaginary numbers in there. Okay, good. So that'll make it invertible. Okay. Next question. Remove a row from A so it's invertible. Right? So I need to make a 3x3 matrix. I need to make sure that none of the rows are linearly dependent on other ones. And I think I intended, so this question was intended to have a 6 here. And this was a typo from a long time ago. This makes it more interesting. Okay. So now there are 2 rows. I need to remove one of those 2 rows because those are basically scale multiples of each other after I've added in this 6. Okay, can you spot the 2 rows which are scale multiples of each other? Yep. The first and the third, yeah. It should give you a hint that the third one was one of them because that's the one I needed to fix. But if I multiply the first row by 1.5, right, this is equal to A1 times negative 1.5, right? So I can't keep both of those rows. What?
That's negative 6. 3 times the negative 1.5.
No, 4.5. Good. Okay. Yeah. Great. Even typo on a typo. Okay, good. Negative 4.5, right? Okay. Then that's a scale multiple of the first row, so I can't keep both of those. It would otherwise I could probably remove any of the rows and it would be a right answer. but that means I need to remove either A1 or A2. So A1 or A3. A1 or A3 are the ones I can remove here, and the rest should be linearly independent. This is kind of painstaking to check usually, so this would be a hard question to ask in a final, something like this, but it's a good review question because we can talk about it here. Okay. Is A transpose invertible? Okay. Okay, what should we look here? A transpose. A is in, it's got 4 rows and 3 columns. So A transpose is going to be, this is a 4 times 3 times a 3 by 4. So it's going to be in 4 by 4. Okay. I know the rank of a matrix is, and I can decompose it into a product of other matrices, is no more than the rank of any of these smaller matrices, right? Each of those are rank at most 3 because they have at most 3 columns. So the rank, the rank is less than or equal to 3. Okay, so is this invertible? A transpose. It's not invertible. So the first answer is no. How about A transpose A? A transpose A is now going to be a 3 by 3 matrix. Okay, and if A is of rank 3, then this will also be full rank. So this is going to be full rank. Okay, you can check its full rank. If I gave you this on the final, I would probably have to tell you that A was full rank, that it was a rank 3. And then this would imply A transpose A is also going to be full rank. And then I can, then it's going to be invertible, right? Following these rules, it's square and it's full rank. The other way you could do this is if I gave you like the singular value decomposition of A, then I can need to reason about A transpose A. And if you remember that kind of inherent components of the singular value decomposition here. If A equals U S B transpose, then A transpose A is going to be equal to U S squared U transpose. The V transpose V, because they're orthogonal, are going to cancel out. And the S is a diagonal matrix. And so I can, if S had so many singular values, then this becomes the eigenvalues, S squared. And if I have no non-zero eigenvalues, then it's going to be full rank. Okay, so that's another way I could approach this. That would involve ideas from eigendecomposition and SVD. Okay, great. Okay, consider 2 vectors. I won't read them all here. Check if U or V is going to be a unit vector. Let's first check V. Is V a unit vector? A unit vector is such that is if a vector R, if the norm is 1. Implicitly, that's a 2 norm. Okay, is V going to be a unit vector? No, it's too big. So not V. Is U going to be a unit vector? Okay, I need to calculate now. I need to calculate U squared is enough. I need to check if this is equal to 1 squared. Okay, and this is equal to 0.5 squared plus 0.4 squared, and so on, plus 0.1 squared, and this is 0.02, what is this? 0.25, 0.16, and so forth, and it turns out the answer is 1. Okay, so U not V. Okay, so U is a unit vector, V is not. It looks like it's got a couple of 0.5s in there and some 0.4s. It seems like it wouldn't be, but if you calculate it, it turns out it is. So you kind of need to calculate these things. This is probably on the upper limit of things we could ask you to calculate, probably more than what I would like you to. Okay, calculate the dot product of U and V. Dot product of U and V is equal to the sum J equals 1 to D of Uj times Vj, right? Which is going to be 0.5 times minus 1 plus 0.4 times minus 2, and so on. Okay, that's what the dot product is going to be. We're kind of running a little bit slower in time, so I'm going to skip the calculations and tell you the answer is 0. Okay, but if there's some minus signs, so sometimes you subtract stuff, positive sign, sometimes you add them. I chose it so they happen to be 0. Okay, so it turns out that 0. Now are U and V orthogonal to each other? Yes, they are orthogonal to each other if and only if their dot product is 0. Okay, so one is a unit vector, one is a much longer vector, but it's in, this is U, this is V, but they form this right angle. Okay, so they're orthogonal. Okay, 8, consider a matrix A. Each row is a customer. There are n customers in the database. The first column is age of the customer in years. Second column is just the number of days since the customer entered the database. Third column is the total cost of all purchases ever by the customers in dollars. Last column is the total profit in dollars generated by the customer. Okay, I'm going to ask you if each of the following operations are reasonable or unreasonable. Okay, first one, run a simple linear regression using the first 3 columns to build a model to predict the 4th column. Okay, let's look at the second one here before we answer that. Use k-means clustering to group the customers into 4 types using Euclidean distance between rows as the distance. Okay, what is this question getting at here? This is a little, yeah. So the different units, right? And if you remember that sign I showed the picture of, you know, it's the miles 42, you know, the elevation 1,000 and the population 700, and then it's had some total, it added these up, 1742, right? So if you're using different units and you're computing like a distance, you're implicitly adding these components up, and that does not make sense, right? So I don't want to do calculated distance if they're if they have different units. So how about k-means clustering, where we're using Euclidean distance? This would be no, this is unreasonable. Unreasonable. How about simple linear regression? This one is fine. I'm just doing a dot product. This is my model. And the dot product, the coefficients we solve for are kind of canceling out the distances. They're turning them into, it's not units. So this one is reasonable. How about doing, PCA, find the best, two-dimensional subspace. This one is not, again, I'm minimizing the sum of the squared errors to the projection. So this is unreasonable. And how about linear classification? And I want to build a linear classifier, build a model. It's the first 3 columns to predict will make a profit, right? Profit is above or below 0. This one's a little bit tricky. It's okay with, perceptron. Okay, perceptron does not measure the distances, but not okay with, say, a loss function, because the loss function implicitly says this point is really misclassified, this point is somewhat misclassified, and that uses a distance. Okay. All right, so this is a tricky, kind of a tricky question for the final. It's important, so I want to put it in the review. Okay, yeah.
So it works out the data history the
Oh, yeah. I would have to specify more, or I would count either answer. Okay. Yeah. So it's not fully formed. If it was a true false question, it would not be fully formed. If it was a free text question, then you could answer this. Yeah. Yeah. I mean, implicitly doing a calculation like this, where I'm adding up things that are unrelated to each other. And if I change miles to inches, I get a totally different answers without changing the data. And so that makes kind of the whole underlying process pretty unreasonable. It's a very common thing. People do this all the time, even though it's unreasonable. I don't want you all to do that after you've taken this course. All right. But you go on the wild and people do stuff like that. They're like, well, why doesn't this make sense? And like, you know, so, all right.
So the underlying thing that makes it easy for whether or not trying to.
Yeah, if I'm using Euclidean distance with different units, if that's somehow embedded in the algorithm, then it's going to be a problem. The perceptron does not use it; it just used misclassified or not. And linear regression kind of cancels out the units in some nice way. So I'd mentioned this during the semester, but I think so you don't want to do these things if they have different units. Sometimes you can normalize them and it's kind of okay, but it's kind of a tricky thing, but it's a very common mistake in data analysis. Yeah. Pretty much, yeah. So when you're doing unsupervised stuff, you can only work with the distance. Sometimes I'm telling you that you give the distance as part of the input. That's usually a modeling step. The PCA we talked about only works with Euclidean distance. So does k-means because of the centering step, basically. But you could do versions of those with different distances, and that would be part of the modeling. And if you said this distance is reasonable because of X, Y, and Z, then you can actually do them. But you need to reason about that distance. Right. So, and that what they're doing here is probably unreasonable to just use Euclidean distance. Yeah. Oh, the mean shift clustering, same problem. It somehow embeds a distance inside of this kernel, and yeah. Yeah. It's hidden at this as you go through your other classes. Keep this in mind. You need to start thinking about to see, is there a distance used or not? Okay. Okay. Consider a data set XY where X is n by 3. Decompose in a test and train set. Assume training is not just a subset of X, but also prepends a column of ones. Okay, so I've simplified it. I can solve for the optimal in the training using this equation. This equation is probably good to remember. That's probably worth writing down on your sheets. I may not give it to you explicitly, but here I've given it to you. And now I'm saying where alpha is in R4. Okay, so typo before, fixed it. The remaining two test data points, X1 and X2, explain a mathematical expression for how to use this test data to estimate the generalization error, right? So how much the expected error do we get on here? How much squared error would we expect? Okay, let me just write down the answer. M alpha of X, this is just going to be a linear model alpha dot 1 X, right? Where I've prepended a 1 onto X, like I said. Okay, and so now the error is going to be the sum of the squared error, M alpha X1 minus Y1 squared plus M alpha of x2 minus y2 squared. And I want to say the expected, what we expect the model to have. Expected expectation, I need to take an average. An expectation on a finite set is an average, so I divide by the number of data points, which is 2. This is the expected squared error. If I wanted the root mean squared error, I would take the square root. But this is the expected squared error, right? This is the expected error. I've squared it, and I've taken the average over 2 things. So that's what's going on in this question. Okay, and this is the linear model. Probably to say, here's a model with expected squared error. Okay. Okay, consider a function f of xy with gradient defined as follows. This is the gradient starting at a value x1, y equals 2, learning rate gamma 1, execute one step of gradient descent. Okay, this is the most important algorithm. So it might be good to know this algorithm. You start at an alpha value of x equals 1, y equals 2. And I want to update alpha. It's going to get the old alpha plus minus the learning rate times the gradient of f of xy. Okay, so the old alpha was 1, 2. Minus the learning rate of 1, that's easy to calculate. Okay, the gradient is going to be x minus 1, 2y plus x. Oh, I actually need to plug in those values. So 1, 2 minus 1 times x is 1, so this is 0, and y is 2, so that's 4 plus 1, so that's going to be 5. Okay, so the result is now 1, 2 minus 0, 5, and this is equal to 1 minus 3. Okay, so that's one step of gradient descent. Okay, this is kind of a decent amount of calculation to do, but this is you should kind of understand some aspect of this question, right? How do we run one step of this? Plus x. This is an x. It's from up here. Yeah, so I had, yeah, y is 2, x is 1, so 2y plus x is 5. Yeah. This is 0, 5. Because x minus 1, where x is 1, is 1 minus 1 is 0. Yeah. Okay. Yep.
In this question, we are given grade.
Probably not. Okay. You know, it's a good skill to have, but not a top line item for this class, right? For a calculus class, probably. But for this class, you probably don't need to calculate the grade of this. Okay. Okay. Consider running gradient descent with the fixed learning rate gamma. Okay. So for each of the following, we plot the function value over 10 steps, right? The function value is different each time, right? Decide whether the learning rate is probably too high, too low, or is so about right. Okay, the first one. We plot 100, 99, 98, 97, 96, 95, 94, 93, 92, 91. Is this too, should I go faster than this, or am I going about right, or is this too slow? Right, so the learning rate then is too low. I want to increase the learning rate, so I'd make bigger steps. Okay, the next one, it's 100, 50, 75, 60, 65. Then I get to 110, 90, 85. Is this too high or too low? Too high. This is where I am jumping around all over the place. I'm making too big of a step. Okay, now I'm at 100, 80, 65, 50, 40, 35, 31, 29, 28, 27.5, 27.3. This is, yeah. This is just right. Right? This is where there's some underlying function, and I'm kind of making these steps, and it's kind of slowing down as it's getting to the minimum here. Okay, and the last one, this is the kind of trickier part. 180, 60, 40, 20, 0, minus 20, minus 40, minus 60, minus 80, minus 100. What's going on here? Too low. Yeah, this is too low. So you should, you don't need the minimum to be at 0 or above. The minimum might be minus 1,000, and I'm making the same increment every step. So it's really the difference that matters. The distance is constant. I should be going faster because I need to get even lower than minus 100. Okay. Yeah, so this is a little bit tricky, but that's okay. Okay, good. Good. All right. Consider matrix A with squared singular values, 10, 5, 2, 1. What is the rank of A? It's an 8x4 matrix. Rank of A. Well, it's the number of non-zero singular values. There are only 4 of them because it's 8x4. It cannot be the rank cannot be more than 1 dimension. So the rank is 4. Okay, what is A minus A2? A2 is the best rank 2 approximation. Right? The rank 2 approximation is basically where I zero out these guys, right? And then I recombine the SVD. So that means the difference between them is what's left, right? It's the part that was zeroed out. And so I can write this as sigma 3 squared plus sigma 4 squared, which is 2 plus 1. Right, so the answer is 3. Okay, if I do the 2 norm, right, this was the Frobenius norm, now we're doing the 2 norm. The spectral norm of this is only the largest singular value, right, of the matrix, but now we're looking at the residual of A minus A2. So the residual is only corresponding with kind of the part from sigma 3 and sigma 4. What's the largest singular value of what's left over? It's going to be this guy. So it's just sigma 3 squared. So that's 2. Okay. What is A spectral norm of A? Right, the 2 norm of A. This is just the largest singular value squared, which is 10. Was the Frobenius norm squared of A1 squared plus A2 squared, so sigma 1 squared, sigma 2 squared, sigma 3 squared plus sigma 4 squared equals 10 plus 5 plus 2 plus 1 is equal to 18. Okay, so I can read that right off the singular values. Okay. V1 through V4 are the right singular vectors of A. What is A V1 2 squared? I put the squareds there to make calculations easier, right? So this is equal to, I can think of this as the sum, well, this is exactly sigma 2 squared. Okay, so it's, I'm looking at the norm, the length of A, once I projected everything onto the vector V2. V2 corresponds with the second singular value, right? So this is equal to 5, okay? Was V1 dot V3? 0, these are orthogonal to each other. And was the norm of V4? 1, because these are unit vectors. Okay, so let A1 be the first row of A. Write A1 in the basis defined are the right singular vectors of A. Okay, so SVD gives you a change of basis, and I want to write it in the new basis. This one is a little bit trickier, but I'm going to write it in 4 dimensions. So I'm going to get a 4-dimensional vector here. The first one is V1 dot A1. The second coordinate is v2 dot a1. The third coordinate is v3 dot a1. And the fourth coordinate is v4 dot a1. Okay, this gives a new four-dimensional point that's in the basis defined by these right singular vectors. Let's change the basis. This is equivalent also to A1 V transpose. I could just write, this will give me the same answer. What? Yep, this will give me a V transpose is the whole the right singular vectors as an orthogonal matrix, right? And multiplying by this will give me this vector. So I can compactly write it in this way as well. Okay, so that's the first step. Remember, the SVD of A is equal to US V transpose, and the first step in multiplying a vector is to move it into the basis so that it's aligned with the singular values. Draw the Voronoi diagram of the set of points. Remember, these are the bisectors of the set of points, and we need to find the closest bisectors. And this is relevant for clustering, where these are the potential clusters here. You know, this one's probably a little bit more complicated than what I'll give you, but okay, should look something like that. Okay, and so the idea is that if you have a point set and these are the clusters S1, then these are all the points assigned to that fall inside of this inside of this region. Yeah, right. Anything inside of this region is what is assigned to S1, and so that's where we need these like Voronoi diagrams. Okay, it's be hard to ask this question on Canvas, but when I gave more like handwritten tests, I liked asking these sort of questions. But okay. What should you do if running Lloyd's algorithm for k-means clustering with k equals 2 and you reach the scenario where the algorithm terminates, right? It got stuck, it stopped running because it did no more updates, Lloyd algorithms. The black circles are data points, the red stars are the centers, right? What should you do? Yeah, you want to do a random restart. Right, and this got stuck because if I draw the Voronoi diagram of the stars, well, those stars are the average of all the points in each half, right? So if I look at all the points assigned here, I intended for that to be the average of those 5 points, and the same with the one on the top. So if I update them, I won't reassign any points. I won't move the average. It gets stuck. I need to random restart, which is randomly choosing another set of initial conditions for the centers, and the hope is that I end up with one center here and one center over here. This gives a much better kind of grouping of the points. Okay. Consider the following loss function. L of zi is 1 minus zi squared over 2 for the data point xi, yi. The prediction function x then I'm still using this trick where I do yi f of xi, right? So this tells me if it's misclassified. Predict how well this might work with a gradient descent algorithm for classification. Okay, what do we want to do here? We want to draw this function of z, identify the 0 point. If it's positive, this region over here, this is, so based on how I defined zi, this is so correctly classified. And this region over here is then incorrectly classified, right? So this is so correct classified. Okay, now what is this loss function? I want to draw a picture. If you have scrap paper, you know, again, great place to draw a picture. This is going to be 0 at z is equal to 1, right? If z is equal to 1, 1 minus 1 is 0, okay? What happens at z is equal to 0? At z is equal to 0, I get 1 minus 0 divided by 2, right? And so in general, I'm going to get a function that's going to go here, and it's quadratic, so it's going to go up like this. You know, I'd like, remember, I wanted to approximate this delta function. And so actually, that's not the delta function. The delta function does this. This is a value 1, this is 1/2, this is 0. Okay, oh, I forgot to draw. What happens right of that 0 point for this loss function? For z equals, if you're not sure, plot it, right? To put in a value, z equals 2. 1 minus 2 is minus 1 squared divided by 2. It's also going to be here at 1/2, right? It's actually symmetric. It's a parabola that comes back up. Okay? Okay, so how is this going to work for gradient descent for classification? Okay, what do we need? Is this convex? Yes, it's convex. So that's good. It will run and it will find a unique local minimum. Does it approximate delta? Kind of. It does okay over here. This part is okay, but not okay over here. Something correctly classified and well classified, a value of z equals 3, is going to be given a penalty. It wants things to have a 0 when they're correctly classified by a value of 1. They want things to have a z value around here. Yeah, this is the value 1 here. Yeah. And so it wants things to have correctly classified at 1, but it doesn't want a larger, better classification. So this part is not okay. It doesn't approximate a delta very well for the well-classified points. And for the poorly misclassified points, so here, this is not robust to outliers. The issue here is that if you have a point which is mislabeled, it has a very large negative value, it's really penalized as well. So you'd rather that, you know, what we wanted are things like, we want things like the, that was going up in a straight line, kind of like the hinge loss. You know, this would be nicer. And so it's kind of tracking along it for a while, but then it's going to shoot up, right? And this part's going to cause some problems. Okay, so those are the things. So this is okay, but it's not so bad. But the gradient's always defined. Also, it has a gradient always defined. So that's good. So this part is good, but these are not great. Okay. Yeah, I know we're over time, but let's just one more question. Consider one-dimensional data points, right? I suggest you draw a picture here. And one-dimensional data points, and they have labels. So x equals 0. I have a plus. Right, that's this point. The next plus, x equals 2. This is 0. 2 is a plus. X4 is a plus. X8. 8 is a plus. Okay, and then for minuses, I've got 1 is a minus. Let's see, 6. This is a minus. 7 is a minus, and 9 is a minus. Okay, I want to consider data points x equals 3, x equals 9, and x equals -1. Okay, I want to do k-nearest neighbor classifier. Okay, so k-nearest neighbor classifier, I pick, let's just do x equals 3 here. I'm going to pick the 3 closest points. I've chosen, so there are 3 well-defined closest points, and I vote. So this is a democracy. The nearby people vote, I guess, or a representative democracy, maybe. These guys, because these are the representative points, they vote, and you get a plus. For this one, for -1, these are the 3 closest. These vote to be plus. And for 9, these are the 3 closest, and this votes, and it's a minus. Okay? All right. Okay. So the last question, if you kind of were following along, you should, and everything made sense, you're going to do great on the final. If something was a little trickier, then that's the part you want to kind of look at a little bit more at. I would try and work on your cheat sheets and write down the core things so you can look them up so quickly. And remember, I'm going to try and ask the very high level things, not a lot of the really detailed things. So you should be okay with time. So try and be there on time and allocate 2 hours. I suggest Monday at 10:30 to be here in the room, or on Zoom would be okay too. All right, I'll see you all Monday. It's been a fun semester.
We don't need to be on the class.
We do not need to be in the class. Yes.
So,